There we go. So we're recording. Okay, Laz, the floor is yours.
Okay, hopefully you can see the main screen.
Yep.
It turned green for me, so it should be fine. Good evening, everyone. My name is Laszlo, or Laz, M0BOY. Most people, as far as I see on this meeting, know me, so no problem. I haven't seen any new faces today. Tonight I'm gonna try to introduce you at a very basic level into what actually an Arduino is. Many people already use it and use it. The people who are actually in this meeting use it at far more advanced level than I do. But let's just try to introduce those who probably just heard of it and never used one, because usually when people hear about microcontrollers, they turn around and just walk out because they have very good reasons for it. And let's say like that 15, 20 years ago, it was a very good reason to just turn around and walk away. If you wasn't really an electronics geek, it wasn't easy to use it. Yeah, so as I said, this was going to be a basic one, but hopefully you're all going to enjoy it, and it's going to bring some new things about these little devices which we can use in the shack very easily, and it's going to be a lot of fun if you introduce it in your radio projects. So what happened a while ago? Some students in Italy at the Interaction Design Institute in Ivrea, Italy, they thought that they could do a little project to create something which it looks like in that picture. That was the very first Arduino created. Hope you can see it and it's big enough. It's a homemade board with an Atmega, an AVR microcontroller with a crystal, a power supply, and a resistor and an LED, and they connected a DB25, which they used to program the bootloader, not the bootloader, but to talk to it through serial port. Well, their target was to create something for, who would that be? For people who are non-engineers. People with no advanced electronic knowledge. However, I will tell you, this doesn't mean it's not suitable for engineers. But what they wanted to create is a way of using a microcontroller for everyone. Back in time, so once again, this is the picture of the very first Arduino created, picture from Wikipedia. When did they do this? In 2005. So it's been a while now, and we'll get to how they evolved as well. What is it actually? It's a PCB, which actually is an open source electronic development board, if you want to name it a bit more in electronics terms, which consists of a PCB assembly, which we're going to call boards, including a programmable circuit, which is the microcontroller, an interface circuitry to allow easy to use programming through serial or USB port. So if you look at it, this is the microcontroller. I don't know if my mouse cursor is visible or not.
It is, yeah.
Okay. Then it's an interface, USB, which in this case, it converts it to serial, UART, but it can be, the very first one was a serial one, so there was no USB. It has an accessible interface through headers and test points for peripherals, so you can connect other devices to it. We'll get there as well. Power supply circuitry with voltage management and voltage regulation. So it will allow us to use the Arduino with nearly every power supply we have around in the house. Obviously not directly into the mains, but everything up to, let's say, 12 volts. So it's a bunch of LDOs there, some capacitors for filtering, some reference voltages for the ADCs, and I think of the 3.3 volt regulator as well, if I remember right. And 2 pieces of software. The bootloader, which is a little software bit of software which is burned into the microcontroller and sets the correct fuses and the correct communication. So it allows us to talk to it in the very easy way with the IDE, which is the actual piece of software we're going to use on the computer. It's called IDE, Integrated Development Environment. It allows us to write the code, to program the Arduino, to import libraries and such. So we'll get a bit more detail a bit further on in the presentation. So this is a very basic block diagram of an Arduino. So as I said, external voltage sources are power supply, voltage management is on the board. There's a USB, which also can be used to power it, some internal voltage regulation, the USB to serial interface, the microcontroller, the headers, some test points and switches, and obviously some LEDs, because there's no electronics which is looking good enough without LEDs. Steve knows. The boards. There are many type of boards. So if you go Google Arduino, you're going to come up with a lot of boards, and it's going to be just confusing. So let's go through them a bit. They are cheerful, very nicely colored small PCBs in various versions, as I said. They include headers to access the inputs and outputs. There's a USB connection, a DC jack for wide input power supplies. There's the in-circuit serial programmer header for both the USB chip and the microcontroller, a reset button, LEDs for debugging. And there you go, a few versions of the Arduino. And the most common and the oldest one, let's say like that, is the Arduino Uno, which contains an Atmega 32 8P microcontroller, whether it's an SMD one or a dual inline package DIP, doesn't matter. They do the same job. They actually on the little nanos and micros, as you see on the bottom left hand side, there is the little SMT Goldwing component, and on the very new one, the MKR Arduinos, this QFN one, which is even more compact. So these are a few examples of boards, how it looks like. If we look at it, we're going to look at it in a different slide to see a bit more. But just a picture of a few boards, a few of the Arduinos thrown on a mat. I didn't do the picture, so it's I just stolen from Google. There's various Arduinos on this picture, and obviously what the difference is, what can they do, and what are their advantages, and what can you use them for. You can go on the arduino.cc website, and all the details are there, together with application notes and all the specifications. So I'm not gonna I didn't include these in my presentation. It's no point. Everything is there online, and if people will have questions of which one to go for and reasons to go for a specific one, I'm happy to answer it at any point. I'm available. Yeah. Okay, the microcontroller. So it's the brain of the Arduino. It's the actual thing. And to be honest, many people just get the microcontrollers, build a very basic circuitry with a crystal and a power supply IC and LDO, and they burn their own bootloader, and off you go. You don't have to buy it. But these days, to be honest, if you go on the very famous next day delivery websites, you can buy a bunch of 5 or a bunch of 10 for 10, 12, 15 quid. So I don't think it's worth building it at home. However, the you know, that feeling that when you build it and you make it work, it can't be bought off the shelf. But yeah, I would go for if I use it for a radio project, I would go for something ready off the shelf. So various boards are based on various microcontroller chips for various purposes. However, the most common ones are the Atmega chips, the AVR chips. And as an example, the Atmega 328P is for the Arduino Uno board. It is an 8-bit AVR microcontroller, which includes 32 kilobytes of programmable flash memory, so plenty of space to write decent code in it. It has 1 kilobyte of EEPROM. It's very good because we can save calibration to it, and it's not lost on power up or power down or power cycle. You can turn it off, leave it there, and then come back, read the values through your variables in the code, and off you go. You have all the details. Very handy to calibrate compasses based on location. We'll get there. I don't want to detail it too soon. 2 kilobytes of internal RAM, a boot code section with independent log bits. So this is very handy to get your bootloader on. 60 megahertz clock frequency, which is quite speedy for what it is. 6 PWM channels, so we have the opportunity to drive motors. Power on reset and programmable brownout detection, which makes it very stable, and it does allow for a robust operation. And a master-slave SPI interface, so we can interconnect plenty of these devices or these devices with other SPI devices. So we can talk things in a very fashion way with very few data lines. And obviously, the very important one for radio amateurs, we have an 8-channel 10-bit analog to digital conversion internal in the microcontroller. Very handy to read values, read voltages, and so on. The software. So we did discuss the microcontroller. We did get to the conclusion that we need a piece of software to be able to make this clever thing work. Yeah, give it life. Let's say like that. The IDE is an open source cross-platform software. It can be downloaded from the website arduino.cc, and it will be used both for writing the code and compiling it and uploading it into the Arduino microcontroller, into the Atmega microcontroller on the Arduino board. Sorry. It is an official Arduino software, which makes code compilation very easy for anyone, even if you don't have the knowledge. You don't have to do anything else than just tell it where your serial port is, where the device is connected to, and make sure your code doesn't contain errors. We'll get there. So if you didn't make errors, you write the correct code, you just push the button, upload. You can verify it first, or you can verify and upload. It goes into the thing gets a reset command, and it's going to run your code. It's going to be very easy to demonstrate on a little sketch we're going to use later on. I mean, we're going to present. I'm not going to do live demonstration. The webcams are not really suitable for that, but I did include a few slides. The IDE, the development environment, is used to communicate with the Arduino, as I said, and convert our code, which is written in C++, into a code which is recognized by the machine, by the microcontroller itself, which would be very difficult for us to write. And actually, an average person won't be able to write it. And back in time, the microcontrollers were programmed in a bit different way. And we'll get there. I'm going to show you what the differences are. These projects, which we write in the little IDE interface, user interface, for some reason they call them sketches. So you write a sketch, which then you verify and compile and upload into the Arduino, and then the thing comes to life with the code, with the commands and functions and instructions you've written here in this graphical user interface. So the sketch itself is, as I said, the name which Arduino uses for the program, for the code, yeah, an uncompiled code. It's a unit of code in C++ that is compiled and uploaded to and run on an Arduino board. It includes all the required information for the program to run correctly. It contains all the definitions. So you define your pin statuses, initial values, and initialize the hardware. So on the Arduino, we need to know that all the inputs and outputs. So on those headers, we will have to define them. So we need to tell it that pin, I want to be an output, and I want to output it by default high, for example. Or the other pin, I want it an input, and I want to read an analog signal on it. So we need to define all of these in the little code. Yeah. So we need to include all the definitions to start with, all the variables. We need to set the type and the initial value of these variables. These are the things that will change based on conditions during the application run. Whoever does programming maybe it's gonna laugh at how I talk about it, but I try to go down to the basic route, to layman's terms. So hopefully it's good enough. Constants, so type of value of constants, which they won't change during the run. We need to do all the inclusions and references to external files such as libraries. There's a lot of libraries. We can do a lot of things with Arduino, and most of the framework is already done. So we don't have to write the whole code. We just use libraries. We include them in framework in our code, and the thing will do For example, driving an LCD, we don't have to actually drive the LCD. We just use the library, tell it to display a character in the specific coordinate, and it's going to do it. And obviously the functions. So this is the clever bit. These are the ones that would run during operation, and they contain all the instructions for what the Arduino needs to do and what conditions to look at, and what triggers and interrupts and all sorts. And obviously every good programmer puts comments in his code, because you come back to it in 6 months time, and you're scratching your head. What have I done here? I can't really remember. So you put a comment there, you say that this bit does this, and this bit whatever, and this matrix contains this array contains that, and off you go. 6 months later, you just look at the gray text, and you know what's there. Compilation, as I said, is a process where a high-level programming language is converted into something the computer understands. The IDE will do this automatically as you click the button, and prior to that, the IDE will check for the correctness of the human written code. I can't highlight it enough how important this is. And the lucky is that you will be flagged for any errors, and not just the flag, but you will be pointed to the line which contains the error. But this doesn't really mean that that is the line which contains the error. Sometimes it's a reference for a variable which you didn't define, or you don't have it, but it will point you to the point where it first time finds it. So it's not like, okay, I have an error in that line. Yes, you have something in that line which won't work, but that might be somewhere else in the code which you need to make the correction. Good advanced programmers know this. It's very basic. Newbies, I would just start with very simple code and deliberately make errors in it, and see how this IDE will point you to your error. And most of the time it's just the bracket missing at the end of the code. So it is important that we have a correct sketch, and not just no errors, because a sketch with errors won't compile and you won't be able to upload it, but one with no warnings. Yeah, the warnings are sometimes very tricky and could lead to unstable operation, or even your software not run correctly, even if it uploads. So for reliability, we want a clean, validated code. Okay, let's compare it. How we write code. Yeah, back in time, if we wanted to display hello world on a, let's say, a serial port, very advanced, very skilled people called programmers were doing this in a very interesting way. It's called assembly. And they were literally defining and telling every bit, everything, where to go, how to. So it wasn't machine code, but it was very close to machine code. So you had to say every little step the program had to do. You had to walk it holding its hands into every step. So we looking at the hello world text here, display hello world, and it's just looking at it how complex it is. I don't have a clue. I learned it at the university 20 years ago, but I can't remember. And seeing this, it just looks complicated. So that's probably good enough for this presentation. It is complicated. However, if we look at on the right-hand side at the Arduino code, we have 2 lines of comments. Yeah, so we already made it even shorter than it looks. What we have a function, which is the setup, and the function, which is the loop. We need to know that, and we're going to get there, what the loop is and what the setup is. Yeah. So I've put in the setup 2 lines, and I told it when it powers up, it runs setup only once, and then it's going to run loop in a loop as long as it's powered up. At every cycle, the loop will be executed. The setup is executed only once on power up. And what we do here is we initialize the serial port, pins 2 and 3, at the 9600 baud rate, because we need to be in sync with what the computer expects. So we can't speak faster or slower, because then we're gonna have the bits is gonna it's not gonna work. And then we tell it to print on this serial port the line hello world. End of. That's it. You compile this, you send it. We have to have the void loop because the ID requires the loop, even if it's empty. You have to define it. You have to have it there. You need to have the setup and the loop. It's the two basic things. So writing two lines in layman's text, or writing this EDX length, the length of a message, define the message. It's way easier, isn't it? So that's why Arduino brought microcontrollers so much closer to people, to everyone, not just highly skilled programmers and engineers. How does it work? As I got into the details a bit too early, but I thought it was necessary to understand how that hello work works. The microcontroller runs as a set clock frequency, executing the program flashed inside its memory at every cycle. As I said, the loop bit. Everything else is going to be run either when it's called inside the loop, or on whatever is in setup, it is run once on power up. For example, most Arduinos will run at 8 or 16 megahertz. We need to be careful, and we need to know what frequency it runs to when we do things which we're going to time. Yeah, because based on this clock frequency, we might end up with half the time we think we put into the program. Depending on the conditions, we set by variables, constants, and whatever we read from pins, from analog pins or digital pin statuses and stuff like that, and interrupts set by hardware like a push button. The code will skip or include additional functions, which we wrote in those lines of code, and we call them in the loop, inside the loop, based on what we, for example, we read the pin and we tell it, yeah, turn the LED on if this pin is high, so sort of things. And then if the pin is not high, obviously that function won't be called inside the loop. It's going to be skipped. So it's, whoever didn't do programming maybe finds it a bit difficult. Whoever did a bit of programming understands what I'm talking about, and the highly skilled people will laugh at what I'm talking about. The Arduinos today are presented for the very basic people, and I'm trying to get this as close as possible, but it's still might feel a bit difficult. We'll get to the examples, and then it's going to be probably more, will make more sense. So everything inside the setup function, as I said, is executed once on power up. That's it. So we don't look at it no more. The code inside the loop function will be run in a loop, as its name states, at every cycle, as long as the Arduino is powered up. Conditions inside the loop function will decide whether certain functions, which we can define them obviously outside the loop, are to be run, so included in the loop, or skipped. So as we had in the hello world, the setup is where your initial variables and you set up your pin initial state, and this will be run only once. The void loop, sorry, it is where you actually put your code, and that runs in a loop. What can it do? So someone called it an interactive programmable logic controller, and I like this. I included it in my presentation. The Arduino can read analog signals, can output signals, whether it's a digital high or low, or it's a PWM. It can do PWM, and that's very handy because we want to drive motors later on. So we need PWM. It can toggle digital outputs and read inputs. It can talk to a peripheral through serial port or even SPI or I2C. What are the advantages of an Arduino? Many people probably sit here today and they just look at me and say, I could do that on the computer, just hook up whatever I need to the serial port, or I could do it on a Raspberry Pi. It's, well, Arduinos are not actually computers. And sometimes you don't need the computing power of a Raspberry Pi, and you don't need the bloated full operating system. You need something very compact, very small, which is also low cost and with low power requirements. We know how hot Arduinos, Raspberry Pis get, isn't it? We know they need 2 amps. So you can't really run it on a battery for a week. However, you can do it on the Arduino. Yeah, you can run batteries for ages. So on a 9-volt battery, depends if it's a basic program and you have no peripherals, it's going to run for quite a while. They are fast for what they are very fast, and they are durable and reliable. You write a very basic code on it, that's never going to fail. They are very small. Some boards are as little as a USB stick. I don't have any around me at the moment, but the little nanos are very small. They're tiny. And they are versatile and easy to adapt to needs, easy to interface. So you wrote a code, you put it in your little box, and to be honest, I always leave room to be able to connect a USB cable to it. I do update my code. I go to sleep, wake up in the morning, have a few ideas, and I implement it, upload it, and I did upgrade the software in no time. So they are easy to interface and easy to adapt to needs. So even if the project is already done, it does what it has to do. And you come up with ideas, it takes minutes for you to implement those ideas. In old man's terms, so we're talking amateur radio terms, an Arduino can blink an LED. Is it useful? Sometimes it is. I would put an Arduino with a blinking LED. Come on, we can buy a blinking LED without Arduino, but just to make it nice and to put some effort in it, get a little Arduino, put a very bright LED on it, and stick it on the end of the beam when you're rotating it in the dark by hand, and you don't need to worry which way the antenna points, isn't it? So it can read and send characters to the serial port. What is this good for? It is good because we can do cat control. It can run as a complex sequencer. All you need to do, use some digital outputs, put some FETs or bipolar transistors, drive them in a specific sequence with different timings, and off you go, you have your sequencer. You just look at an input pin for the PTT. When that is high, you tell relay 1, go on, 100 milliseconds, relay 2, go on, 100 milliseconds, relay 3, go on. And when the PTT is released, you do it the other, whichever way around you want it, off you go. Very easy to implement. It can be your antenna rotator, can it? Does it have enough computing power for an antenna rotator? It does, I'm telling you. And it can be, as I said, a CAT controller, a CW keyer or decoder. Hoppa, hoppa, the senior members already raising their eyebrows. It can be an accurate RF power or SWR meter, provided you have the proper bridge. Yeah, and you can use the ADCs to convert the voltage into numbers and so on. It can be an antenna switch. You can do a remote switch, a very clever switch with Arduino. You can interface it with Bluetooth, and you don't even need cables. All you need is power on the other end, and you can get a power much easier than run a long serial cable out in the garden. That's a bit, it's lossy, and serial doesn't like to be very long. So it can also be an antenna tuner. Yeah, you feedback the SWR as above, and you tell it to flick some relays in specific order until that SWR goes down, and off you go. And with some extra hardware, it can be a full radio. Okay, we didn't talk about the headers, the interface. I'm going to quickly go through it because we looked at the board earlier, then we went to software, but now we want to think a bit out of the box and go a bit further than the actual Arduino. These things can do a lot more with additional hardware, with a little bit of external help than they would do on their own. So these headers, hopefully the picture is big enough. They have a lot of little sockets there, which will allow you to access different signals. You can access power pins like internal reference voltage. You can access a reset pin. You can access voltages, obviously ground planes, and obviously the analog pins. So you can use the ADC converters, and you can use the I2C. You have two ICSP headers. You can program the bootloader with an external programmer. You can program the USB chip with an external bootloader. You have a crystal, and you have the SPI pins, or whichever, you can use them as PWMs. So depending on what you define in the software, in the definitions, what to use the pin for, you can use it for either SPI, or you can use it for to be a PWM output, and so on. You need to be careful that only a few pins can be used as PWM. So if you, the red one says that, the red text here says that only the pins denoted with the ampersand are PWM supported. Not ampersand, whatever is that character is, the like the AC waveform. Yeah, you can't use any pin for any function. You need to make sure you use the correct pin for. There are pins which can do digital, analog, actually digital or analog, but there are some digital pins which can do PWM. Others can't. So if you define the wrong pin, you expect a PWM, it won't do it. Yeah, you have pins which can do I2C, pins which can do SPI. Also, you need to be careful that only some pins will do SPI. You can't use any pin for SPI. So through these headers, because we have such a wide variety of signals accessible, we can add additional hardware. We can interface the Arduino to other little bits, which they will call shields later on. So going back a bit to this board here. So we have 5 volts and 3.3 accessible. We have the analog pins accessible, the digital ones with 6 PWM enabled pins. We have SPI, reference voltage access for the ADCs, direct or through USB serial port access. So we can access the serial port through the USB or through pins 1 and 0 here. It might be that we do something, or with the USB we screw it up, or we don't have a computer with USB. We can still use the serial port. We have a in-circuit serial programmer header, actually 2 of them, as I said, a reset button, so we can toy with resetting it, see how the code. Anyway, a lot of fun. We can add additional buttons if we want. So there are LEDs for serial comms traffic. There are 2 LEDs which will show you whether the Arduino talks to the computer when you're uploading, so you can debug in case it's not, and an LED for on pin 13 for debugging, which you can do programs on and check whether it drives the LED or not. On its own, as I said, it is basic, so it doesn't really do much, but it's down to imagination and the available boards, which they call shields, on how we can expand the functionalities of Arduino. So through these headers, which contain the analog and digital inputs and outputs and all sorts of voltages and other signals, we can interface a lot of additional hardware, which, as I said, they call shields, to extend the functionality of the Arduino. Examples: Ethernet shields will allow us to interface it with our own local area network. Relay shields are useful for amateurs to create a sequencer, for example, remote controller, push-to-talk for amplifiers, and so on. Proto shield can be used for easy prototyping. We have it here in the middle, so you have just like a breadboard sort of a shield, and you can make your own little circuit just poking the components in. Very easy to validate designs. Motor shield with LM298 bridge, which is very useful to drive DC motors and create an antenna rotator. LCD shield, which we can include in our projects to display information about what's going on inside our box. These are various types like OLED or LCD or 2-line or 4-line or even graphical interface, graphical displays. So we can use them to display information from our sensors connected to the ADCs, obviously, such as SWR, power, temperature. Whole weather stations are built on Arduino. Michael M7SOIN knows about it. GSM, GPRS, Wi-Fi, Bluetooth, GPS. So whatever wireless thing we want to do, we have the opportunity. Human interface, device interfaces, buttons, joysticks, touchpads, NFC, RFID, so near field connection, conditional access, and all sorts of stuff we can do with Arduino, no problem. We'll see now a few examples of these shields. The picture is not the clearest in the world, but as an idea, on the top left corner, we have a touchpad. Then we have something, I don't really know what that is. Then it looks like a Wi-Fi hat. Then we have some prototyping hat here with an SD card, so we can interface SD card, another prototyping one. Down here, we have a joystick one. We have the breadboard one, which is very obvious, even a camera shield. I think that's a radio, if I look right. There's a variable capacitor here, a display, some sensors, gas sensor here, an NFC, RFID one here. Hopefully my mouse is there. A GSM, GPRS one here with a little antenna, and a CAN interface. No, this little one down here is a CAN interface, so we can even use protocols used in vehicle, and obviously the well-known 16 by 2 lines display interface, which is so commonly used by amateurs. All right, let's get to real examples of how can we do things with Arduino. On the left-hand side, we have an Arduino Uno, a resistor, and an LED. So that's our BOM. And on the middle, we have the schematic. On D13, we connected a resistor and an LED. And on the right-hand side, what we do on the setup side of code, we say that the built-in LED built-in pin, which is pin 13, you can also define pin 13, is an output. So we want to be driving the LED, not look at what pin status is. And then inside the loop function, we write a digital signal, which on the LED built-in pin, which is defined up on the, which is actually defined as an output, we put it high. So we turn the LED on. Then with a delay, we wait for 1,000 milliseconds. Then we turn it off by putting that pin in the low state. Then we wait another second. And what happens after the loop function is finished, it's going to start all over. We need to make sure that we don't use the delay function unnecessarily in our code, because this will use an interrupt, and this means that all of the other code execution is suspended during that 1 second and obviously the other second. So our code is going to be waiting for 2 seconds. Instead, we're going to use counters, and when we reach the specific counter, we action the pin status change. So it's much easier, and obviously we can run the code while we're waiting for the LED turn on time to lapse. But this, when you use counters, you need to make sure that you do your calculations based on the clock frequency, because otherwise it's not going to be. But the Arduino IDE has a solution for that, and it makes it very easy, because all you need to do is you use the milliseconds, and it's all good. All right, a bit more complex. We read the pot, and we on an analog input. So what we do here, we use an ADC, an analog to digital converter, which actually turns voltage into numbers. For whoever doesn't know, an ADC turns analog signals into numbers. So a 10-bit ADC, as we have in the Arduino, will convert 0 to 5 volt range into a signal ranging between 0 and 1023, providing a resolution of 4.88 millivolts per count. And whoever is fancy, 0 volts means 0, and 5 volts means 10 times once as bits. Let's quickly look at the code. So we define that we have a potentiometer on pin 2 as an input. We define that the LED is on pin 13, and we say that the value of the pot feedback, the voltage fed back by the pot, initially is 0. Then, as a setup, we say that the LED needs to be an output. Otherwise, how can we drive an LED? Then inside the loop, we change the value of var, which is a variable, based on what we read from the potentiometer, from the pin which the potentiometer is connected to. Then we turn on the LED, wait for the amount of time the var is read from, depending on the position of the shaft of the potentiometer. Then we turn the LED off, and then wait for the same amount of time again. So by rotating the potentiometer shaft, we will vary the voltage on the ADC input, which will lead us to a different number for the variable var, which is the value. This will mean that we will turn on and off the LED based on the voltage on the ADC input. So that means turning the pot shaft will increase or decrease the speed of the blinking of the LED. So this is a very basic representation of how an ADC works. Yeah, how we can use an ADC. Sorry, we literally feed that variable voltage into that pin, and the Arduino will change the value of VAL and the timing for the LED based on that. So it will action based on the value of the voltage on that specific pin. Let's take it to the next level, because we are amateurs, not in the real meaning. We are radio amateurs, so we want something more professional, and we want a bit more complex thing to do here. Let's take an LM298N bridge. Oh, I went the wrong way. Let's take an Arduino Uno, two DC motors, geared to DC motors, so we have a bit of torque, an I2C compass, and a handful of jumper wires. And obviously, find or write a suitable sketch, which is a program. What can we get out of this? It's an antenna rotator. Simple as that. Two motors, a motor driver, an Arduino, a compass for the position feedback, and a handful of jumper wires and the code. And this is the fully built rotator by Michael. Thank you for the pictures, Michael. I think he's here listening. Mike 7 Sierra Yankee November. And we're going now to the point where MCARS members did something. As you can see, is the LM298 driver here, is an Arduino, is the compass with accelerometer and gyroscope as well. It's a complex I2C chip, it does everything. On the bench, here it is already boxed up, and the same night he was already hunting for weather satellites with this box, with this antenna rotator, all interfaced up to the computer. Going forward, another little project, very easy to write the code for, a bit more difficult to build it and design the PCB and everything. It's a sequencer, which was built by Phil, G4FVZ, and as far as I know, it does a very good job, and it's very simple, few transistors, an Arduino Nano. As you can see, the USB port is accessible, so if he has some ideas or wants to improve, just connects the USB, uploads the new code, off you go. I was toying here with the SARCnet rotator. I still have it, and I'm still going to finish it. Actually, I did rotate a piece of aluminum bar with it, but not actual antennas. Here in the middle, I was experimenting, and as you can see on the right-hand side, I was experimenting with using Bluetooth as serial port. It works pretty well, so I won't need any wire. Just connect this little Bluetooth thing, push that button on it, pair it with my computer, Bluetooth, and once that is done, it can go in a box. That's a little Arduino Nano or Micro, whichever. As you can see, based on the size of the USB, micro USB connector on the cable, how small it is, and you can do the same thing as with a Uno. It's probably a bit less pins to access. And here on the right-hand side, after I wrote the code, it was literally mirroring the traffic from the serial to the Bluetooth, and whatever was coming on the Bluetooth was outputting it on serial. So if I was writing on serial, it was outputting on Bluetooth, and the other way around. So other radio projects. This is a list of what others did from the internet. So they did an RF signal generator, VFO, AM/FM radio receiver, APRS tracker, AM transmitter, MKR Fox weather monitor, a very complex weather station, S-meter for ICOM and Yaesu radios. You can find the code for it. You can find the schematics for it. External display for FT818, 817, based on Arduino. even DAB radios, and oh, it's going the wrong way, the wrong direction. SDR radio, even with Arduino, and obviously SWR and power meters. And the possibilities are countless. They are unlimited, obviously restricted to the computing power of these microcontrollers. All the information about how to start with, what do you need, how to work, tutorials, very basic introduction in how to do sketches. It's available on the arduino.cc website. That's why I didn't include much in my presentation. I tried to explain a bit more rather than reproduce what's already on the website. However, there are dozens of Facebook or Group.io or Hackaday.io pages. Also, you can join. You can just have a look, or just stay in the background and watch, or just talk to them and ask questions. And as I said, possibilities are countless, and I can guarantee you it's a lot of fun. Okay, thank you for attending tonight, and hope everyone had a good time. If there are any questions and I can answer them, obviously I'm looking forward to them. But I'm not an expert in Arduino. Again, I do stuff which probably many of you do at a very more advanced level. But yeah, I'm happy to answer any question if you have any. And thank you again for listening and for the patience.
Thanks very much indeed, Laz. That's really fascinating talk and a great introduction to Arduino. Does anybody have any questions at all, or questions for Laz at all?
Yeah, I had one, Chris. I'd been playing with the little one, the Nano, to interface to some old rotator, Yaesu rotators, and I've got it working, which is great. Quite fancied having a play. I've done some odd changes. Got a reasonable understanding of what coding is doing, but I'm not a coder. But are there examples to look at for reading pins and writing pins and shoving things up, analog to digital converters and odd bits of code? Because trying to interpret the one program that I have got, which is the rotator interface, it's kind of a bit more complex than I was expecting, and I'm not sure the guy has put that many comments in to explain what he's doing. So is there something that we could look at
yeah, obviously, if you send me
be a bit simple?
If you can send me the code, Chris, and you know, I can have a look at it and add some comments to it and send it back to you. So even line by line, or where the analog reading is happening, I can add some comments for you to know what's happening at a specific time in the code. So that's not a problem. And yeah, for the analog read, for example, it's very easy, because you read the status at a specific time, and then you store that value in a variable, and then you read it again on the next cycle, or whatever, when the time is lapsed. And obviously, if you wanted to make it robust, you add some filtering on it, some averaging, so you don't read spurious values which might not be real if you have some noise. So you can put some filtering on it. But yeah, if you have the code, I'm happy to have a look at it and put some comments in, and even discuss it line by line, if you know, at some point.
Yeah, I wasn't trying to decode everything that particular application is doing, but just trying to understand.
Well, we can focus on
simple
activities
that that might make sense to play with. If I want to start writing anything of my own, but I didn't find anything that was an obvious, here's the place to start. There's been the odd book produced for Raspberry Pi, but I didn't find anything for the Arduino.
The Arduino.cc quite nicely explains the analog read and stuff. But yeah, if you have it in a code, it might not be the tidiest code in the world. And yeah, if you drop it to me, I can have a look and just concentrate on that particular area of how it's read, and probably, you know, putting some comments on that specific area and explain it to you will make you understand way better than you do now. So
Chris, one book I use for doing code is, I don't know if you can see it. I'm sort of
It's an
trying to,
Arduino something.
yeah, it's Arduino for Dummies.
It's
Oh,
been
okay.
printed out.
Okay.
If you look in the IDE for each board, there's generally examples for each type of function, and so that they will give you a simple example program to for every functional group that each individual board will do, and that's a good way to learn how to actually incorporate that into a larger scenario.
Where am I looking for that?
If you look under the IDE, I think it's under examples.
Actually, in the IDE.
Yeah. I don't use the Arduino one, so I'm not very familiar with it. But
yeah, I didn't include that in the presentation, but yeah, the ID contains a lot of examples and a lot of libraries, and you can import them. Didn't want to get into too many details because I had the feeling that the presentations will be too long. But whoever has questions about it and wants to know more, I'm happy to help at any point.
Okay, thank you. I'll have a look at the IDE. That's really what I was looking for, examples just to have a look at. The other thing I found with the way I was building things was that you can buy a board to plug your Arduino into that has, instead of the header pins, which are a bit of a pain to play with, ordinary sort of chock block terminal connectors with a screwdriver slot in them. I found that quite useful. That wasn't on your list of boards that you can get.
Well, I did give a few examples, but as I said, most of the shields and everything is it's the possibilities are unlimited. So people come up with ideas every day. So probably my list, even if we would have been complete yesterday, would be outdated today.
No, it's just a thought for those that want to play with Arduino. It just makes connecting to it a bit easier if you've got lots of wires to other boards.
Well, you can buy these jumper wires so far. There's millions of them, and I don't know, I like them, but yeah, not everyone likes them.
Yeah.
So.
Any other questions for Laz at all? Just a show of hands, you know, who's messed around with Arduinos and got them working and all the rest of it. So quite a number of us, you know. Really.
Yeah, that's what I said. Probably they're more experienced than I am, so they just got bored today.
It's all experimentation. You know. But the thing that's always surprised me about them is they always seem quite robust in RF applications. They just seem to work, you know, irrespective of what RF is kind of floating about. They doesn't seem to actually be effective.
Yeah, they are immune. They're very reliable.
They're really good, very good.
A lot of very good error correction as well.
So, anybody?
So, you know, what have people used them for in their projects?
Well, as I said, yeah, I can share the screen again. So
no, you know.
Oh, these people.
People around here.
Okay.
What have you used, you know, them for, or are you still learning and gathering the skills to apply them? Oh, I'm sorry.
Yeah, let's hear a few projects which I haven't had in my presentation because all I knew is antenna rotator and sequencer.
I'm happy to kick off just to start. So you saw the little sequencer, the FET sequencer, which I use for sequencing antennas and LNAs and all the rest of it. And all the Arduino does is to switch things on and off at the right time. And you can adjust it by software, which is what I liked. That if I hadn't quite got it right, there were too many times to adjust. I could just keep playing with the software until I had the timing right. And that's why I use that.
Looks a bit easier than Mr. W6 PQL's, lots and lots and lots of transistors.
Yeah,
and a few ICs.
You know, you're in and out, as Les showed. You know, you whack a cable into it, you're in and out with the software, and you know, you're screwing the lid on again of the thing within probably 5 minutes, and off you go. You know, it's really good. So that's one application, you know, that I made. What's the latest one? I've got one where I built a data interface, and it did all the timing and the PTT switching and stuff for a data. Some of the homebrew stuff I did needed a data interface, and so it provided a data interface and did all the control on the data interface and the PTT and the switching and the timing and stuff. And I used an Arduino for that. So there's a couple of things that I've used them for. Well, lots of people put their hand up.
Well,
Who's next?
I use mine for sort of monitoring temperatures, pressures, humidity, and movement in different rooms of the house. A bit sad, but it was a project to sort of gain knowledge, and that then integrates into a Raspberry Pi for the display of what's going on.
Okay. So Michael, M7SYN, he's shown his rotator for his weather satellites, and Chris, you've built that Arduino-based rotator controller.
Yeah, it's an interface so I can use Minos with old rotators that don't have the nice Yaesu code interface that talks to Minos. So you have to build something in between the two. So I can read my rotator and tell my rotator where to go to.
Anybody else made stuff with them?
I haven't made anything as yet. I've got a few Arduinos kicking around. I'm one of those people who used to use assembly language years ago at college, and I bought some PIC processors to play with years ago as well, and I got into assembly language with those, and I thought, this is a waste of time.
Life is too short.
It is, and you know, you downloaded the microchip IDE and, you know, programmed PICs using C. And then it's just, I think a couple of years ago, I bought a couple of Arduinos off eBay and thinking, what's all the fuss about? And it is, you never have to reinvent the wheel, ever. If you want to drive an LCD display, there's a bit of sketch or a library to do it. You want to read something, there's a library to do it. Every problem you've got has been solved by hundreds and hundreds of people before, and there's a massive, massive community out there. I can't think of any reason I'm going to use a PIC for anything, you know, basic, like, you know, building a cable tester or something like that. I'm not going to use a PIC for that anymore. Next time I do it.
Yeah, once I used an Arduino, I quickly programmed it to make it a programmer to program a 3D printer. And I found the code online, and it was just off you go. And I had to write a bootloader onto the 3D printer to accept the code through USB, and that was it. Used an Arduino to do the job, so didn't have to buy a programmer.
And the open source code is generally extremely reliable.
I mean, that's it. But the two other things I like them. One, I've never blown one up. I've never had a doff one. It's so I've got a box of them still and go through them, and they're so cheap. You know, as you say, you get them from Amazon, and you get 5 for £10 or something. They're really very cheap, the Nanos. And the other thing is all open source, so it's almost like anything's up for grabs. It's just there's so much there to beg, steal, or borrow against to get something working.
The only thing they're difficult for is debugging your code, because the standard Arduino interface won't give you breakpoints and sort of watches on variables. That's the only, you know, platform I/O. Yeah.
I mean, Michael's just saying even the Chinese copies, which I'm sure I buy the Chinese copies, even they don't blow up. So it's remarkable, really, you know. On that.
Yeah, that's probably what I have, a bunch of them, and it's just, they work.
Yeah.
The only small thing I found is that there are some types you have to, when you load the IDE with the program, you have to tell it which which Arduino you're going to. And there's generally lots of libraries that you access to sort of get bits of code in to do things. But I found that some of the obscure ones, the very, very small Arduinos, I forgot what they're called now, actually. They've got
nanos.
No, there's some smaller, they've got some smaller than the nanos.
Blimey.
And they're about half the size of the nano. Can't remember what they're called. And
can't remember either.
but the libraries on them is quite limited, so they're much more of a challenge to get something working. Is that you probably can't find a library to do what you want. You do have to work it out, but that's the exception rather than the rule.
Has anyone used MicroPython on them?
No, not yet.
Oh, we have a yes.
No, I said not yet.
No. We do have a yes
Yeah.
from Mike. Okay.
Yes, I have on the ESP32.
Yeah.
I mean, you can use it on the ESP. Yeah, you can use it on the ESP. What's called 3286.
Yeah.
But I would use the ESP32 that has more memory.
Okay.
So it's fun to learn a way to learn Python actually.
Yeah, that was my thought. It's it is a way to learn. You've got to kid yourself you're doing something useful.
Yes, certainly.
Even though you're not.
Yeah. I'm actually starting to use more of those because they have Wi-Fi, and for some of the stuff I do, I want a fast connection. So, and as someone else said, the interference they don't give out enough interference, and they are at least on HF you can toast them, to say it that way, without anything happening. In worst case, I had the Nano locking up a few times, just reset the power remotely, and that's it, and it works again.
Right.
So the current project is a Nano, which I use to control one of those LDG tuners. So basically build a remote antenna and antenna tuner and switch. So it's just a prototype. I'm probably going to make a PCB later when I have time. Time is always the problem.
Yeah, that's the most expensive bit of it.
It is. So I thought I was thinking buying one of those remote LDG tuners, and then I thought, why? When I can get a cheaper one, and then just make an Arduino to do exactly the same thing. It's half price probably.
Yeah.
Or even more.
Steve, you were showing us something there you built with an Arduino, weren't you?
It's basically an interface between 817 and PC. It's got cat control both ways, and it's for working on the satellite Q100, and you can add an offset in with it, so that if you're using SDR radio, for instance, and your transmit is slightly offset, you can just dial in the offset. Also, when you transmit, it goes back from the FT817 to the SDR radio and mutes it. So you don't have, the howl round or echoing as you'd normally get, that sort of blows your mind.
Right.
So it's quite handy that way. And if you want a net, you just press the button and it will unmute it, and then you can adjust it, and then press it again and it'll mute it. But that was somebody else's code that I butchered. Actually, it's full of faults. It didn't work to start with. And it's quite useful. I mean, it uses the RS-232 out. Sorry, it's not RS-232. Well, it's RS-232 into USB, but then you need another RS-232, and you can just get a bit-banged version that you bring in as well. So you can get two RS-232s out, even though the device has only got one. And as per SPI and any of the others, so you can get the big bang versions.
Yeah, I've done something similar for the Q100 but on Python on the computer. But yeah, this sounds nice to do it with Arduino.
Yeah, I just wanted something that was standalone.
Do you get the power from the radio?
No, it's got external. Sorry, where does power come from? USB.
From the USB.
Yeah.
Oh yeah, because you want.
I can't remember. It's
it's
been a few months, but yeah, it comes off the USB from the PC.
I was toying with the idea to do something similar with and use the split function and to compensate like satellite mode with Arduino. So just have it plugged in the back of the radio, and when you turn the knob, it adjusts the VFOB based on on the offsets you set initially.
Yeah, I guess so. That displays the frequency you're on and the offset that you've got applied.
Yeah, you can adjust with a button, with a knob.
Yeah, with a knob, yeah, with the rotary encoder. Yeah.
Just perhaps the last thing this evening, Michael again has messaged, just highlighting the new Raspberry Pi Silicon Pico, which really looks to me something that's akin to an Arduino. And apparently, as I understand it, the two are going to talk. There's software that can be able. The two are going to be able to talk to each other, and you program in one, it will program the other. Really, on that.
They're going to do an Arduino, and they're going to write the Arduino code for it, so you'll be able to use Arduino on it.
Right.
So in other words, it'll just be like a Uno or a Nano, but you'll be using the Pi version. And they, of course, they're low cost, and they've got two processors on them. So one generally does the I/O, and one does your code, runs the core code.
Okay. Anything else this evening? Well, just thanks once again for that. As you generate a lot of discussion, a lot of interest, and you know, many of us really couldn't use the Shack without having an Arduino somewhere to do some of those things. And thanks for taking us through us and introducing us to those this evening, Laz. So thanks very much.
If anyone has questions, I try to answer them. You know, I'm not an expert, but yeah, I can help.
Laz is there, so PM him if you do have questions, further questions. I guess it's difficult to perhaps show our applause and appreciation, Laz, but just a big thumbs up from all of us. That's a really excellent presentation, and we'll publish the recordings. So thanks for that. Two more messages on chat, both thanking you this evening for your talk, Laz. Really good. Thank you. So the next, we may have a social kind of get together next Monday. I've got to look at the program, but the next formal talk is the talk on Solar Cycle 25 with Carl, and I've forgotten his call sign, but the guy from the States who's going to be connecting with us. So we look forward to that. Thanks, everybody. Have a good evening. Stay safe.
Thank you.
Bye.
Bye-bye. Take care.
Thank you very much.
Really good. Thank you.
Bye.
Bye-bye.